Today I'm going to do a walkthrough of some of the limitations of machine learning and artificial intelligence methods as they are applied to time series forecasting and projection. My tools today are going to be Monument AI. I'm going to use Mathematica to generate some waveforms, and I'll load the data up in Excel. And I'll go back and forth between generating the data, saving it out as Excel, and then importing it into this Monument toolkit. The first thing I want to do is talk about the origins of time series forecasting and projection in order to understand what some of the problems are with it. So we can look at the most recent O'Reilly book, and by the way, I have no ill will or hard feelings toward anyone whose papers I may reference in this video. There are quite a few papers out there. There are some really good books. This is a big field and a big topic, and just because I've highlighted one particular author or team doesn't mean I'm calling specific attention to them. I'm really referring to the field as a whole. So this is a book that was just published. This was published fairly recently. I think it was 2019. And it talks about practical time series analysis, prediction and statistics with statistics and machine learning. And in this book, one can see the table of contents refers to, first, obviously, some visualization, a quick overview, some data preparation, simulation, data storing, but then it gets down to forecasting using machine learning. So there's some basic things like deep learning, some machine learning, then on to deep learning. And using some basic neural nets, CNNs, RNNs, the future post-RNN would be LSTM. They probably deserve their own category, but then boosters and other things. Measurement error, etc., and some applications. Now when you get to the time series packages, a little pet peeve of mine is the fact that most people focus primarily on Google and Facebook, and they ignore some of the great work done in the other toolkits, such as MATLAB and Mathematica, and even C. So this is a book, and you can see that there are some frustrated folks talking about this. They're generally frustrated with the length of the book, but they're also frustrated with articles I tended to like. There is a lot being discussed now in 2020, and I expect this to pick up on Introduction to Time Series. Here's a great article from 2018, How Not to Use Machine Learning. And this individual is talking primarily about the fact that stationarity adjustments and time series basic statistics can determine whether a time series is a random walk or not. And if it is, it's probably not something you can forecast. If it's not, then you might have an underlying predictive model that you can determine. On YouTube also, there are some speakers here at this qcon.ai InfoQ. Here's a speaker discussing decomposition. First decompose, in this case, he's using a fast Fourier transform, and he decomposes the waveform. Here's another speaker talking about a couple different applications from Uber, and this one is a Azure advertisement discussing Jupyter notebook connections to Azure to do some time series modeling. There are even ebooks you can buy for 37 bucks, and this one goes into LSTMs. This is where it ends. You can go here, and most people will talk about the problems with models. In general, machine learning and AI are spoken about in time series projection and modeling in terms of LSTMs and convolutional neural nets. And just to show you some really up-to-date results, here's the Cornell Archive website, and I've just typed in time series forecasting. I've opened up some of the results that show up on the top page. Here's one that talks about Bitcoin. They're comparing RNNs, ARIMA, and of course the time-tested LSTM. Here's another one, was published. And then if I scroll down on this one, we're of course talking about their extension of prior work from 2019, again using long and short-term memory networks, LSTMs. So the field is awash with LSTM type analysis. And let's go back in time to talk about where that came from. So LSTMs do fairly well with basic problems of predicting recurring patterns. A typical pattern is a sine curve. And this is because LSTM can predict over a series of samples. In this case, a time series window would be moved across this time series. Maybe you'd take 10 or 15 observations at a time and feed those in to a neural net, and it would learn that pattern of 10 to 15 points. So if it would take this 10 points, for instance, it would notice that anytime you saw these 10 points, it would tend to go down. Maybe every time you saw these 10 points, it would tend to go up. And so a sliding window of 10 points would go across this. A challenge, unfortunately, is that LSTMs were not designed to do more complex waveforms. And that's what one of the YouTube video speakers was discussing. And here's a very clear example. Adding a sine curve to a sawtooth results in something that looks like this. And this is a great example of something that has too many patterns for a simple LSTM to predict. So what you would typically see is this waveform will be broken down into a high frequency component and a low frequency component. And that's what this YouTube speaker here was essentially doing, decomposition by fast Fourier transform. You might see EMD, VMD, CEEMD, various methods like that used today instead, especially in quant finance. So an LSTM will be stretched to do this, but could be helped with some decomposition. An LSTM will classically fail on a high frequency, low frequency. That's what this decomposition is designed to do, but you can trip it up even more by feeding it a sawtooth. You can get it even more complex when you throw that on a trend. So here's a very simple example that will choke most AI modern algorithms in the time series projection. Unfortunately, this is just too much for an LSTM. An LSTM trained to detect the high frequency noise here will do an okay job at that high frequency, but will not see this overall trend, and that's where it will struggle. Likewise, we could trip this up even more by taking a curve like this and then adding to it a sawtooth. Here we might have this sawtooth, and just to visualize this on its own in Mathematica, we might do something like this. And we can see that this sawtooth added to this waveform will end up getting something like this. And if we plot that from a data perspective, it'll look like this. We could trip this up even more by taking this and maybe adding a separate one, something like a sine, saw line. And maybe what we can do is we can make it a little bit more aggressive in slope. And so here's our component for slope. Here's our sine, let's see. And here's our component for slope here. So we could do something more like this. Let's add this is a second line. All right, and so here we have a slightly more aggressive increase. What we could do is magnify potentially the effect of the sawtooth, and perhaps minimize the effect of the secondary wave. So here we've got something a little bit more easy to see the recurring pattern. It still has that high frequency sine curve built into it. So we'll call that sine line, saw line 2. If we can take this, we can simply take this set of data and just, for those that are watching this maybe not as familiar with Mathematica, here's what that data looks like. We've just got a row of data, the top 10, the first elements of that. We can take a look at the rest of it. Looks like that. So we've just got an array of figures representing this data line. And what we'll do is we'll take this, copy this out, add this to the end of our data, and then what we'll do is we'll add this as a new element, we'll call the sine sawline 2. Save that as a CSV to our test file. What we can do here is we can load that test file up. Let's see, make sure we can save this. Save this to desktop. And here we go. So we've got sine line 2 on the line, and should be able to add this. So what we'll do is we'll save this as the new formatted data. We'll save this out, and we'll be able to load this up. So what we've just done here is we've just added this. This is our formatted data. We could look at this formatted data, maybe the top 10 rows, and we'll notice that this is simply a matrix of data with the date formatted in the first row, the first column, and the values for the sine, the dense sine, etc., in all the subsequent columns. And we'll take this and we'll save this out, and this just is saved. This just gets saved to this test file out here. When we open this up, we see this in Excel. This is the same data, simply updated in Excel. We'll close that, bring that down, go back to Monument. Input, we will take the CSV, we'll double click on test. That will reload it. When we see it reloaded, we see the sine, the second line added, and we can see that. Okay. Get back to our interface, columns X. We'll have the date, and here's the original line, and here's the secondary line. So here, what we just implemented in the waveform, we can now see immediately replicated side by side into Monument as a tool. So we have this one line, which was the original one that goes up to 8. Then we have the second one, a slightly more aggressive trend, and these additional waveforms. Okay, so now that we are in Monument, we can then load up some of the other lines. The very first thing we could do is we could throw on an auto-regression. Now, an auto-regression could be thrown onto sine, the original line, and we can throw another one on to the secondary. So what we've done right here is we've just dragged, I'll do that again slowly, we've dragged an example onto this, we've dragged an example onto this. Okay, so finance in general would have initially spent most of its attention on auto-regression based methods, and these AR methods tended to evolve into the types of analyses that we saw in the archive papers earlier, where the individuals were doing ARIMA, so maybe ARMA, ARIMA, maybe generalized auto-regression with GARCH. Models like that will tend to be in this AR family of models, and they tend to be momentum-based. They both are doing okay, predicting that there is going to be some periodicity to this line. And that's where most people will spend their time and energy. But let's see how this performs with the sine that we just created, this the sawtooth plus sine on a trend plus a high frequency sine. What we'll do is we'll go ahead and throw in this LSTM, a short look ahead period, maybe a small batch size, and we'll do training epochs. We won't run it that long. We'll do 200 perhaps. And then we'll go ahead and throw this on as an LSTM. That will take a little bit of time to run. We'll let that run. And we'll see very, very quickly what I wouldn't say this is the state of the art, but I would say what the publication activity on a site such as Archive, as we're looking at time series forecasting, what they're doing, they're spending an awful lot of energy writing papers on something that we'll see in a second is probably not the state of the art. So that LSTM has just finished running, and here's basically what it's looked like. So you can see it understands a little bit at this training epoch. Obviously, we can tune this significantly. It's understanding that there's some dip that's happening. It's not really understanding when that happens. At this point, it didn't have enough data. It had 2 of these observations, and so it knew that every time it saw one of these spikes, it would tend to go down afterwards. So it learned that here's this spike, it'll go down, but then it got thrown off. So the LSTM in general knows that things are going up, but it's getting thrown off by the conditions. Here it looks like it's memorized this one. Okay, so the LSTM hasn't done so well, and this is the ARMA family. Just as a reminder, we can zoom into that and be convinced that the LSTM and the ARMA, the auto-regression family of algorithms, are both in general seeing that there's a dip as the next prediction point, and then they're both generally going up. The auto-regression has some idea that it will then recur. But now let's do something that is far more accurate, and that the models don't have us, the papers rather, don't have us seeing in the modern day, which is something like this. So we can stick an entropy booster on there. Let's turn off auto-regression and LSTM. And we can see that this waveform here, in this case, has learned that there is a recurring pattern and that there is a waveform. Unlike the auto-regression and the LSTM, however, at the moment, we can increase the accuracy of the entropy booster by go ahead and turning on some additional independent data, such as the sawtooth, the sign on the line, and these trends. And we'll see that now the entropy booster is getting much more accurate. It's doing things with its trend at this point that the LSTM couldn't possibly hope to get. And the LSTM doesn't have nearly that look-forward ability. It's also doing something that the auto-regression is getting, but the auto-regression is missing that there's this other trend that's sort of cyclical here. We had this these cyclical phases going. And so just within a few clicks, we can see that this entire space that is currently focused on LSTM deployment and tuning, and I generally notice that most of these LSTM algorithms tend to be out-of-the-box configurations from Google and Facebook, and they do run into some of these problems. We can see that this is an awful lot of attention focused on something that within a couple clicks we can already outperform on this tool. I'll put the links to all the sites that I've referenced and mentioned in the description of the video, if anybody's interested in checking those out. And I'll also put a link to this file that I've generated. And I will put a link to the Mathematica file that I've put together here so that you can make some additions to these types of data and waveforms that typically break algorithms that are categorized as artificial intelligence time series projectors.